Great.
Okay, so this is our Mocs Assignment 2 submission, group Jack Durio and Ryan Langlois, and we decided to evaluate the relationship between Lotka-Volterra equations and a stochastic cellular automata rule set for multi-level ecosystems. We wanted to see if we could reveal the same underlying system dynamics. So we have two systems, which is food chain and omnivore predator. Food chain is exactly what it sounds like. You have three trophic levels which prey on each other, and then the omnivore predator is like grass, rabbits, and foxes, but the foxes can eat grass and rabbits. Rabbits can only eat grass. So scrolling down to our rule set of our food chain model, we have periodic boundaries in a Moore neighborhood where 0 is empty, 1 is grass, 2 is rabbit, and 3 is fox. The grass as an index will just spread to one random empty adjacent cell. We have evaluated a time step as the time guaranteed for grass to spread to a neighboring cell. Rabbits will attempt to eat a random grass neighbor. If there is no grass neighbor, they will die with chance beta. And if there is a partner and both the partner and the index cell are neighboring grass, they will reproduce with chance alpha. Foxes are the same thing, except they die with chance gamma, and they reproduce with chance sigma. So running down to the video, you can see here that it doesn't look at all like a two species Lotka-Volterra cellular automata. You get these weird islands of stability with the foxes, and they don't really sweep around like how a two population model would. And I believe the reason for this is that once a agent is born into a cell, it cannot move from that cell. It either keeps reproducing and eventually dies in that cell, or immediately dies in that cell. So you get this weird play between the three trophic levels where foxes are spawned in as an initial population, and then rabbits reproduce around them, and then the foxes eat the rabbits, but don't eat enough rabbits to reproduce so much that they can expand. The grass then will fill the space created by the foxes from eating the rabbits, and the rabbits then eat the grass there and keep the fox islands alive. So you get this really cool little spatial dimension play. And unfortunately, this is inconsistent with the numerical analysis of some papers. So if you can scroll up just a little bit, Ryan. There's a inequality which held beta over 1 plus gamma over 1 less than 1. All three populations should be stable. And this stability point is globally asymptotically stable, which essentially means that for any point in the space, if you approach the point, perturbations are ignored. You can see from this graph, though, that if beta is 0.2 and gamma is 0.3, that inequality does hold and the foxes immediately die out. I believe this is because the spatial dimension adds just too much difference to the simulation to be comparable with the numerical analysis.
Moving to the omnivore model, we simply modified the existing framework so that foxes will view grass as potential food just as much as rabbits. This produces some interesting behavior, as you can see from this graph, as well as some of these. There's some standard typical behavior seen across initial parameters. For one, the foxes and grass tend to oscillate more so than the rabbits and grass in the previous example, and the rabbits population tends to generally decrease. This seems to be because the foxes outcompete the rabbits. Foxes have 2 potential food sources, while rabbits only have 1. And there was one particularly interesting example when rabbits' reproduction parameter was equivalent with their death parameter, and the population died out. The result was the most pronounced oscillation we've seen in one of these, and that seems to be due to the reduction to just 2 species again. Again, it's similar to Lotka-Volterra, but not quite.
And so our ultimate conclusion for our research question is that even though we would like them to be comparable, and there are aspects of them that share the same underlying dynamics, the added addition of a spatial dimension in the simulation throws off the numerical analysis too much to be true in most cases. Thank you.